Hello, everyone. I'm Dr. Usman Tariq. Uh, I'm a faculty member in the Department of Electrical Engineering in the American University of Sharjah. So thanks a lot for the organizers for inviting me over to give this talk. So what we're going to talk about today is a basic introduction to artificial intelligence and deep learning. Okay. All right. So let's start. So let's first ask ourselves that what is artificial intelligence, right? So there have been several definitions over the past. For example, making computers think, creating machines that can perform functions that would otherwise require intelligence when performed by humans, making computers perceive, reason, and act, and so on and so forth. Okay. Now, when you see, these days you might be, when you see the media, you hear like a lot of buzz about AI and artificial intelligence, right? So many times you would want to know that, the thing that you're discussing right now, for instance, is it actually using artificial intelligence? Or you may be interested in knowing the answer to the question, is this AI, right? So for that, I found this very interesting, page from this MIT technology review. So that gives like very interesting, insights about, different things. Let's suppose, you start with this sort of an algorithm, right? If you may ask. So you say, you start here, right? You can see my pointer, right? Yeah, okay. I'll assume that you see my pointer.
Yeah,
So anyways, yeah, okay, that's good. So you start over here, right? You first ask yourself the question, okay, can the thing that you're looking at, can it see, right? If the answer is no, right, so then probably you go back to the start and start the question again. All right, so let's say you start the question with something and you are interested in knowing that you ask the question that can this thing see. If the answer is yes, all right, now then you may ask the question, can it identify what it sees, right? If the answer to that question is no, so then what you're looking at is just a camera, right? It's just a camera, it just takes pictures. That's it. So it's something that sees, it just takes pictures, right? All right. Now, then if you go back up right here, and then you again ask the question, can it identify what it sees? If the answer to that is yes, like for example, behind the camera, there is another algorithm that is telling that, okay, there is, let's suppose, a chair in the scene, a car in the scene, a person in the scene, etc. So then this indeed is using AI, right? And the thing that is using, is known as essentially computer vision and image processing, right? So this indeed is using AI, right? Good. Now, yeah, right. So let's go back to the same question again and to the start point. And then let's suppose you see something and you want to know, can that thing hear, right? Well, if the answer to that question is no, right? So, okay, then you go back again, right? So let's not consider that. All right, so you ask the question, can it hear? Then yes, okay, if it does hear. Now, you may ask the question, does it respond in a useful and a more sensible way, right? If the answer to that is yes, right? So then you may ask, then you see that yes, if it's responding in a useful and a sensible way after listening to something, so that is using a branch in artificial intelligence that is known as natural language processing. The example of that you might have seen in Amazon Alexa, right? You can ask some question to Amazon Alexa, it's listening to you, right? And once it listens to you, then it's going to respond in some manner. Since it's listening and it's responding in a useful and sensible way, this is using AI. So this is natural language processing, and then indeed this is using AI. All right. But if you go back to this question, does it respond in a useful or a sensible way? But if the answer to that is no, so then you may ask the question again, that is it transcribing what you say, right? That means, if it's writing, it's recording in a textual form what you're saying. If the answer to that is no, so then it's just a mic. Like, for example, a mic here, I'm just saying something. It is hearing, right? but it's not responding in a useful or sensible way to my commands. It's not transcribing what I'm saying. So for that reason, this is not really using AI. However, if it is transcribing what I am seeing, for example, I am saying something and the closed captioning are automatically generated, right? So yes, this indeed is something that is known in artificial intelligence as a speech recognition, right? And this indeed is using AI. Okay. You might have seen some examples of that, let's suppose in cell phones, right? So you have, when you're typing something, many times there is like a microphone icon. So you can, press that icon and you say something and it would transcribe what you're saying, right? So that indeed is an example of artificial intelligence in use, and that is the branch of artificial intelligence that is known as speech recognition. All right, so, you go back and then you again ask the question, can the thing that you're looking at, can it read, right? If the answer to that is no, all right, you go back to the start thing. But like, let's suppose the answer to that is yes, right? So then if it is it reading what you're typing, right? If the answer to that is yes, right? So then does it respond to in a useful and sensible way? If the answer to that again is yes, so yes, and that is indeed using something that is known as natural language processing. An example for that is like, you are typing a command, right? And then, like, for example, you may have seen chatbots, right? You are talking to chatbots by sending some messages, and they respond by, in a conversational like manner. So yeah, that is indeed using natural language processing and artificial intelligence. All right, now if if it's not reading what you're typing in, but it's reading the passages of text and trying to analyze, let's say, some patterns in the text. For example, if you're looking at reviews on Google or Yelp or let's say Zomato, right? If you want to analyze automatically that the review that you have that someone has written, is that a positive review or a negative review, right? So if you're doing that sort of analysis, so yes, indeed, this is something, this is an artificial intelligence machine which is performing on natural language processing. Okay, another example, can something, you're looking at something, you ask the question, can it move, right? If the answer is no, maybe you're just looking at a dumb object. Now suppose you're looking at something that can move, right? Now then you may ask, okay, can it move by itself without any help? If the answer to that is no, right? So then, that may be just a dumb robot. You just pass in command to the robot, okay, go right, go left, go straight, and it responds according to those commands. Doesn't have an intelligence of its own. You're giving it the commands by yourself. So this is not using artificial intelligence. However, if it can move based upon what it sees and hears, right? And it's not going on a pre-programmed path. So yes, then that indeed is a smart robot, or that indeed is using artificial intelligence. An example of that are these days, you have vehicles that can drive autonomously or semi-autonomously. So those indeed are using artificial intelligence. Okay, so with this, slide, we just understood to ask our question, to if you're perplexed to know that if something is using artificial intelligence or not. So maybe we can ask this series of questions, and that can let us to the conclusion if something is using artificial intelligence or it's not using artificial intelligence. Anyways, now generally when you talk about artificial intelligence, the thing that comes to your mind is something like a Terminator, right? The Terminator, if you have seen the movie, I don't know if a recent version came out recently, but back in the days, this was a thing, right? So the artificial intelligence that the Terminator has, that is something that we can refer to as the general AI, right? What does it mean from the general AI? That means you want to mimic the same characteristics as human intelligence. You want to perform the same things as humans can do, right? You want to react the same way as humans do to certain inputs. You want to design stuff. You want to extract rationale from things that you see and hear, and you want to make intelligent decisions. So that is what we refer to as general AI. We are not there yet. Right? We are trying to achieve that, but we are not there yet. But what we have achieved really well so far, we can refer to that as narrow AI, right? These are essentially the technologies that are able to perform certain specific tasks as well as, or even better than what humans can do. One example for that can be, let's suppose, you see a picture over here. There are algorithms that can identify which part of the picture is a face. You might have seen also in your consumer grade cameras or in your cell phones. You take out your camera, you look at the scene, it can identify, okay, this part in the scene is a face. So probably you need to improve the quality of that certain specific region. So that is an example of artificial intelligence, or the technology itself is known as face detection because it's detecting faces in the scene. Now you can go one step ahead. In addition to detecting faces, you can find out whose face are you looking at. For example, here, this is these three actors are from some movie. I remembered the name like maybe a couple of days ago because I saw it and I totally forgot it now. Maybe you know the name of the movie. It's about vampires and those things, right? So coming back. So in addition to detecting the face, can you then tell which person is who, like who is who in the picture? That is something that is known as face recognition. So for example, here the algorithm can tell, okay, this guy is Ian Somerhalder and this guy is a male, so you can also identify attributes. This girl is Nina and she is a female. This guy is Paul and he's a male, so you can identify the faces. You can find out who is who in the picture. You can find out what attributes do they have. So this is an example of narrow AI. And computers have surpassed us in many of these applications. For instance, face recognition, right? We as humans, we can remember a finite number of faces, right? But for computers, there is no limitation. They can remember millions of faces, right? So for that reason, you might have seen applications of that happening. Like, let's say you exit some of the airports here in United Arab Emirates. So at the exit gate, it just looks at your face or your iris in your eye, and then it lets you go, saying that okay, this is you, and you are exiting the country. And when you enter, for example, there are some smart gates, and there you stand at a certain place, you look at a certain camera, and that is basically recognizing the iris in your eyes, and then based upon that, it's telling which person is who, right? Or is it recognizing the face and taking the picture for future reference. So these are examples of narrow AI, and in these applications, we have developed technologies that are able to perform different tasks either as well as humans or even better than humans. And this is the reason you see the buzz of AI in media these days. Okay, now when you talk about artificial intelligence, right? Then you might have also heard the name machine learning, right? You might have also heard the name deep learning, right? How are these related? Now, if you see about these terms, AI, that's artificial intelligence, machine learning, and deep learning, you can think of these as like, a stack of Russian dolls, right? You have a doll within a doll and within a doll, right? That kind of thing. So similarly, you can think of them as like three circles, right? Each one is inside the other one. So the big circle around here, the big circle here is essentially referring to the artificial intelligence. That is a more general, term that refers to anything or any aspect of artificial intelligence, right? But then a big subpart of that is something that is known as machine learning. So what is machine learning? In machine learning, we refer to algorithms that have the ability to learn without being explicitly programmed. Like, for example, you want to recognize an object in a scene, right? Like you want to recognize if in a certain part of the scene there is a car, right? Now, cars come in many different shapes, colors, right? Orientations. Like, for example, yeah, like this is one car, right? Uh, this is another kind of car, right? I'm really great at drawing, so you get the idea, right? There are different models of cars, there are different kinds of cars, and based upon the camera position, the image that you take may be very different from the other one. So you cannot write a computer program with all the instructions to recognize where the car is in the image. So what you do in machine learning, you gather a lot of data, and using that data and certain algorithms, you let the algorithms learn by itself that what is important to recognize if in a certain region of the image there is a car or not a car. Okay. So then essentially machine learning refers to the algorithms that have the ability to learn without being explicitly programmed, without being giving the instructions, okay, if the object looks like this or looks like that, that is the car. Why we cannot do that? Because there's so many possibilities. We cannot enumerate all the possible possibilities. So what we do, we gather a lot of data, and we have algorithms, and we let the algorithms come up with the features or important aspects that define a certain object, and with that we can do object recognition, or in this case vehicle recognition. Okay, now then a subset of this machine learning algorithms, we have something that is known as deep learning, right? What is deep learning? Deep learning is, so this is a glass, and this is really deep. Deep learning is basically something that is very deep in learning. What do I mean from that? In deep learning, you are learning the useful features or useful information from the data in the form of hierarchical representation, right? You have different layers of learning, right? And one particular example that comes to my mind is like, as you go progressively in the depth of the algorithm, you will be learning increasingly meaningful representations. For instance, if you looked at the vehicle recognition example, so the initial algorithms may be just learning that, to identify if there is a certain edge of a certain orientation of an edge, or like, some spots, how to recognize if there is a certain region has like a corner, right? Or like there is an edge, or there is like, some inclined edge, and so on and so forth. But as you move deeper in the algorithm, you will figure out that the algorithm is learning complex representations that are a combination of these simpler representations. For example, after a couple of layers, you may be beginning to learn like parts of the car. You may be beginning to learn, some things that are able to identify, let's say, parts of the wheels, and so on and so forth. Right? So that is where deep learning, is very powerful, because since it's learning the useful features or useful informations by itself, and it's learning in a way that it goes progressively from simpler representations to more complex representations. So this is what this gives the edge over traditional shallow machine learning. Okay, and these algorithms have really surpassed in a number of applications these days. You name it, and if it's using AI, it's a good chance that deep learning has improved the performance above the traditional machine learning. Deep learning really helps in those kind of scenarios where you have a lot of data, right? When you have a lot of data, you have a lot of things to learn, right? And deep learning, since they have millions or billions of parameters, they can then learn themselves from that lots of data that can consist of images or sound files that are hundreds of thousands of hours long, and so on and so forth. Okay, so bottom line, when you talk about machine learning, AI, and deep learning, AI is like more general area, and then machine learning is a subset of AI, and deep learning is a further subset of machine learning. Then what we talk about machine learning, what is machine learning? If you want to look at like sort of a definition, in machine learning, you program computers to optimize a performance criterion using some example data or past experiences, right? What does it mean, right? Let's suppose you want to identify between, let's say, apples and oranges, right? Uh, so if you want to identify apples and oranges and you want to do that automatically, one way maybe, you gather some sort of measurable quality of apples or oranges. For example, you find out the circumference of the fruits and let's say the weight of the fruits, right? And then you give it to an algorithm. And what the algorithm is going to do based upon the circumference or let's say the weight of the fruit, it's going to learn how to classify which input is what, like which fruit that you give as input is either an apple or an orange, right? So that learning of knowledge that happens with some data that you give it, right? You do not explicitly say, okay, if the circumference is bigger than 5 centimeters, you say it's an orange, right? If circumference is less than 5 centimeters, you say it's an apple, right? Why? Because these general rules do not, you know apply in real life, right? Real life is much more complex. Real life is much more complicated. It has a millions of rules. So those rules machine learning algorithms learn automatically. Now if you talk about deterministic processes, for example payroll, you know there's no need to learn such deterministic processes. Why? Because let's say if you take the example of payroll, how much an employee is going to earn, let's say per hour, and how many hours the person worked in a month. Just multiply that with the hourly rate, you get the person's salary, right? There's no learning needed over here. When is learning needed? Learning is used when the human expertise do not exist. Like for example, you want to navigate on Mars, right? If you take the example of Mars rover, right? If you want to give a command to the Mars rover, there is some delay, and that is more than like 8 minutes. You give a command, and then it comes back, right? The result comes back to you, and you give a command for the rover to move forward. But after let's say 8 or 10 minutes, you found out, oh, okay, I arrived at like in a valley or in a ditch. So that will be too late, right? So what we needed to do then, so we made it able to navigate automatically, right? Looking at the surroundings, it would find its path to go to a certain place. So machine learning is definitely used over there. Machine learning is used when humans are unable to explain their expertise, like let's suppose speech recognition, right? Not so long ago, and even now, we don't know what are useful characteristics for speech recognition, because when we record a speech and when we see the speech, it's just a sequence of numbers, right? And how to extract what features are useful, right? We have come up with some probabilistic features earlier, right, that were used for speech recognition. But recently, you might have seen that speech recognition performance is massively improved, and that has happened because of deep learning, right? Because now we had millions of hours of data, and we had algorithms that were powerful enough to extract automatically what is useful to recognize speech, right? So that is how we improved our speech recognition performance. And in speech recognition, you do need machine learning. Then there may be examples of solutions that may change over time. For example, predicting which route is going to have more traffic so that you avoid that route at a certain time period, and so on and so forth. So these are the examples in which machine learning is indeed useful. So if you take some examples of some tasks that are best solved by machine learning, recognizing patterns, recognizing anomalies, and predicting stuff, like what do I mean from these things? For example, if you talk about recognizing patterns, you want to recognize objects in real scenes. You want to recognize, okay, this part of the image contains a chair. This part of the image contains a person, right? You want to, let's say, recognize facial identities. You want to recognize faces. Who is who? You want to recognize facial expressions. If the person is in joyful mood, or is nervous, or is annoyed, right? So, and also you want to recognize like spoken words in speech recognition. Now, The other example in which is best solved by machine learning is about recognizing anomalies. And what do I mean from that? Anomaly is something which does not normally happen, right? Now, it's such a term which is very difficult to to define, because something may be considered anomalous in a certain scenario and not anomalous in another scenario. An example can be, let's suppose this is you, right? And you are in, let's say, in your school, right, in the corridor of your school, and you are running, right? uh, that may not be that normal, right? However, you can think of it, okay, that may be a bit normal. But if you see someone like crawling right inside the school, right, going on like this, that is really anomalous, right? But if, however, crawling outside when you are trying to cross, let's say, a hurdle, right, in a course, right, so that is not anomalous in that scenario. So anomaly depends a lot about on the context in which you're trying to define if a certain thing is anomalous or not. And here machine learning comes to our rescue, because it can come up with rules automatically that can define if certain thing is normal or abnormal in a certain scenario. One example can be if you have unusual patterns of sensor readings in, let's say, a nuclear power plant, right? Some things may be off. Yes, they may be individual sensors which you can look at one by one, but if you're like thousands of sensors, how you can combine the information from those thousands of sensors to find out what or what combination of those readings is anomalous and what is not. So that can be done by machine learning. Another example can be prediction, right? How to predict, let's say, the future stock prices. I mean, still, when you predict stuff, there is some error, right? If there was no error and you can predict the future perfectly, so then I would have been a billionaire by now, right? I mean, you can predict the stock prices, right? How the stock is going to perform, let's say, in the next week or so. But again, there is some error. Right? There are some companies that look at news data or Twitter feeds to analyze if there is some positive sentiment or negative sentiment for a certain company. So based upon that, they can predict the stock prices of that company can go up or go down, right? You can also, with machine learning, you can identify which movies will a person like. Right? It's a very interesting problem, by the way. You see your Netflix, right? You have seen, let's say, a TV series, right? You have like a score. If you are scoring through different TV series or movies, you have a score which tells you, okay, how likely are you to like a certain movie, and how do they come up with that? They come up with that based upon the attributes of the other movies that you have seen, and based upon the movies which other persons have seen, and they have seen a particular movie, which you are looking at, you're deciding whether you want to see it or not, and they sort of, predict based upon the other person's behavior and your behavior that whether or not you're going to like a movie. And when I'm talking about behavior, that refers to your past, watching history, what kind of movies or what kind of series you have seen before. You might have started a series, but you just stopped in the middle. That means you may not like it, you switch to another series, right? But if you have seen a series like in a continuous form, like from one first episode to the very last episode in the last season, that means you're really into that season. So and based upon these kind of things and user ratings, you can predict which movies a person will like or not like. Now we talk about machine learning, how it is done. You may ask how it is done. So what do you do? To do machine learning, we essentially need three things. We need the input data points, right? Let's suppose if you talk about predicting apples from oranges, you would need to gather lots of apples and oranges, right? And based upon that, you can classify which one is apple, which one is an orange. Then you need intended outputs. What does it mean? If you, let's suppose you want to classify apples, this is an apple, right? This is an orange. You want to classify between the two. Let's suppose you gathered 1,000 apples, you gathered, let's say, 1,000 oranges, right? And you have this data, right? These are the data points. The characteristics that you extract from these fruits are the input data points. And then those characteristics, to what fruit do they belong to? Let's suppose you extracted certain characteristics from an apple. The label or the intended output is like, okay, these characteristics are for an apple, or these characteristics are for an orange. And then using this information, you can, there should be a way in which you can measure whether the algorithm that you're trying to learn is doing a good enough job or not, right? And that is what we do in optimization. Then there are different fields that are useful in machine learning. For example, in statistics, since statistics deals with doing an inference from a sample, right? So here we are just dealing with lots of data, so statistics is important. So many of the machine learning models are essentially statistical models. And then computer science is important because you come up with efficient ways to to solve the optimization or to improve the algorithm, right? Or to improve the parameters of a model such that it can do the intended task. Okay, now we discussed about the example of apples versus oranges, right? And so if you want to classify automatically, if let's say this is an input fruit, whether this is an apple or an orange. So to do that, you have, let's say, a model, right? This is suppose a model. And how have you learned the model? You took, let's suppose, 1,000 apples, 1,000 oranges, and you extracted some characteristics from apples and oranges, right? Like, for example, one characteristic can be, let's say, the circumference. I'm taking an example, it's not generally how we do it, but this is just an example, right? One can be the circumference, the other can be the weight of the fruit, right? So this way you can have, let's say, weights and circumferences of 1,000 apples and weights circumferences of 1,000 oranges, right? These measurable qualities we refer to as features. For example, here we are gathering two features. One of them is a circumference and the other one is a weight. When we gather features, we can organize them in sort of a vector. So this is a feature vector. So it has two features. X1 feature, for example, is the circumference, and X2 feature is the weight of the fruit, right? Now, if what is a feature, like we discussed, is essentially an individual measurable property or a characteristic phenomenon that you're being observed. Right? Now, choosing good features is a crucial stage in machine learning, right? Because, if you have good features, you may be able to classify things in a much simpler way, right? Or a much easier way. Now, how do these features look like then? These features, once you have gathered them, they're just numbers. So if this has two dimensions, so this is essentially, so one fruit can be, let's say, just a point in a two-dimensional space, right? So if you have 1,000 apples, so they may be these 1,000 points in this two-dimensional space, and 1,000 oranges may be these points in this two-dimensional space. And maybe you would want to come up with, let's say, a classifier or a separating, area that can separate the two, the features from the two classes. Okay. Yeah. So, and that you do after you have gathered these features. Now, like we discussed, like just a moment ago, that choosing informative and discriminative features is a crucial stage for machine learning. And this is where deep learning comes in handy, because in deep learning, we are combining the the feature representation learning and classification, or whatever thing that you want to do with the model in one package. So in deep learning algorithms, we can extract these features automatically, right? So that is what it makes it so powerful, right? So here we are just learning successive layers of increasingly meaningful representation. And how many layers in a certain model, that contributes to the, that is what is referred to the depth of a certain model. Okay. Now, if you think of, from a geometric perspective, what is deep learning? Just imagine if you have, let's say, two pages, right? One is, let's suppose this is in red color, this is an orange color, and you just, crumble them up together, right? You make them into a ball. right? And suppose on one of the page you have classes, you have items from apples. On the other page you have items from oranges, right? The points on the other page represent oranges, right? Since they're all crumbled up together, you cannot easily separate them together, right? So what you can do, you can maybe come up with slow geometric transformations and unwrap that crumbled up data, right? And then once it is unwrapped, then it's very easy to separate the two classes. Okay, so this is what deep learning can maybe thought of doing from a geometric perspective, right? That it's just demystifying or reducing the complexity of the way your data is distributed in some space. Okay, now if you talk about neural networks, you might have heard about neural networks. What are neural networks? Neural networks are essentially are modeled after brain, right? And most of deep learning algorithms are based upon variations of neural networks. Now, these were initially inspired from the brain, but now things have moved much farther. And the concept of neural networks dates back to even to 40s, when the first mathematical model of neuron came along, and that just made the basis of neural networks. If you talk about neuron, so what is a neuron? Right. So far we've discussed about artificial intelligence, the basics. We discussed about what is machine learning, like just a rough idea. We discussed about deep learning, right? We discussed then about how neural networks are related to deep learning, and the basic fundamental component in a neural network is a neuron. What is a neuron? Neuron is, in case of a brain, is a basic brain processor, right? These are nerve cells, and they transmit signals to and from brain, right? And the speed of transmission, they're very fast. It can be 200 miles per hour. And each neuron cell communicates to anywhere from 1,000 to 10,000 neurons, muscle cells, glands, and so on, right? The number of neurons in our brain, if you take a wild guess, it's even bigger than your wild guess. We have around 10 to the power 10. That means 10 billion neurons in our brain, right? Most of the neurons that the person has are already present at birth, but they make and break connections as they, learn stuff. If you look at a general structure of a neuron has these, three basic components. You have, let's say, the cell body, which is this one. Yeah, this holds the DNA information and the nucleus. You can think of it as the brain of the neuron, right? Then you have these dendrites, right? All these connections. They're generally short. They are taking information from other places, and then you have an axon, right, which is coming out of the cell body, right, and it's very long and it may split into thousands of branches at the very end. They can be as long as 1 meter long. So what happens? A neuron is accumulating information from the surroundings, right? And a very simplistic view of a neuron can be when that accumulated information exceeds a certain threshold, then the nucleus sends a spike throughout the axon, right? So this can be a simplified version of a neuron. You are getting some inputs, that is signals from other neurons or some other sensors. And then you are performing a weighted sum over here, right? So let's suppose this is weight W1, W2, W3, W4. This is, let's suppose, feature X1, X2, X3, X4. So here you're performing W1, X1 plus W2, X2, and so on and so forth, right? And when the sum is bigger than a certain threshold, you just, pass a spike through the axon body. That can be thought of as, let's say, the value 1 to the axon body, right? Okay, now this thing that when the accumulated sum is bigger than a certain threshold, that you pass a spike, you can think of that as a very small decision, right? The neuron body decided to send a spike, or in our case, our model decided to send a 1, right, or something close to a 1, when the input accumulation is bigger than a certain threshold. Now, these small decisions can be combined together in something that is known as a neural network. You can have neurons connected to other neurons and those connected to other neurons, right? And all of them, by making these small decisions, are making a joint decision, which is something big. Like, for example, recognizing if there is a certain object in the scene and so on and so forth. Now, if you look at a simple neural network, it may look something like this, right? You have, let's say, a simple neural network. You can think of that as composed of three layers. You have, let's say, the input layer, then you have a hidden layer, and then you have an output layer. Now, each one of these hidden layers, you can think of them as neurons. Why? Because these have connections to these inputs, right? They are performing a weighted sum. So all of these connections have weights. For example, this W1, W2, W3, this maybe have W100 and so on and so forth, right? So all these connections have weights. So this neuron is connecting, is gathering a weighted sum of the inputs. Let's suppose you have inputs X1, X2, X3, X4, X5, right? And when the input is above a certain threshold, it outputs a 1, right? Or something close to a 1, right? And otherwise, it stays at 0. Then at the output layer, you also have neurons, right? Now, these neurons in the output layer, you can think of them as decision-making entities. For example, each neuron can be specific to a certain class. Let's say you want to classify between cars, persons, and let's say chairs, right? So you have three classes, right? So these output decision units are specific to these classes. And when one of if the others is this is high, you say the input that you saw was a person. If this is high, you say okay, the input that you saw was a chair, and so on and so forth. Okay, but all of this is happening by accumulating a weighted sum of these inputs, right, in these neurons, and these neurons make some small decisions, and those decisions are combined at these output units, and that helps you decide, okay, this thing is a car, this thing is a person, this thing is a chair, and so on and so forth. Okay, and what are these inputs? These are features like we discussed, circumference or the weight in apples and oranges, right? They have two features. In this example, we have, let's suppose, 5 features, and so on and so forth. What's a deep neural network? In a deep neural network, you have multiple hidden layers. You have multiple layers of these hidden neurons. So how does it help then? We have seen that as we go deeper in the network, since those small decisions are combined into increasingly larger decisions, so we learned meaningful representations of the input as we grow deeper in the network. This is an example of a deep neural network. Then there are other variants. For example, this is an example of a deep convolutional neural network. Again, it's trying to learn features. What are features? Those weights. The weights are the features that the model is learning, right? Or the parameters of the model. And this is being learned, and all of this at the very end is going to tell you what was present at the input. You can have recurrent neural networks. Those are specialized for sequence processing, but those itself may require, let's say, 3 hours to understand. So I'm not going to go through that. Now, you may ask, okay, these weights, we discussed all of these connections have these weights. So how do you learn these weights? You learn these weights, by formulating a cost function. Like we discussed earlier, you need to have a criterion that can tell you if your algorithm is doing a good job. Now, what can that cost function be? There can be several different examples. One example is, let's suppose, this is the output that you're seeing at one of the nodes in the neural network, and this is what the output should have been, right? Let's suppose here, the output that you're seeing is 0.6, and the output that should have been at this node is 1. Right? So then you're doing some sort of an error. So what you can do, you can see how much error that you're doing across all of your inputs, and then that is going to give you that how good or bad your algorithm is performing. Right? Now these outputs that you see over here are dependent upon the weights in the model. Right? So then what you do, you use this cost function to update the weights in the network, or update the weights in the model, right? Such that to reduce this error, right? And the algorithm that we do use that, we use to achieve that is known as the backpropagation algorithm. So, just a very crude example, suppose this curve is showing you the loss, right? So, and the values of the weights are lying on this axis. So suppose you start from this value of the weight, right? And you see to which direction should you move such that the value of the loss decreases. And you figure out, okay, this is the direction you should move to reduce the value of the loss, right? So let's suppose you arrived at this point then, right? And then from here, you see which direction should you go to increase the value of the loss, to decrease the value of the loss, and then you decide accordingly, and so on and so forth. Okay. All right. I have some example of TensorFlow Playground, but probably, I'll see if I have some time at the end, where you see an actual neural network working, right? But then bottom line is deep learning has achieved numerous breakthroughs, in many different areas which were historically difficult for machine learning. For example, near human level image classification, near human level speech recognition, near human level handwriting, transcription, and so on and so forth. There are several fields that deep learning has impacted. Now, let me quickly give you some of the examples of my work, but I think this is a good idea. Before we go there, let's spend like 1 minute on this link that I showed you here, which was playground.tensorflow.org, and let me share with you my tab, right? So I guess can you see my my browser? Yeah, I guess you can see my browser, right? Okay, now here, for example, we have this example neural network. These are the inputs. You have these 4 neurons at the in the hidden layer, and these are the output 2 neurons. And the data, let's suppose in 2-dimensional space, is distributed like these points, right? You have 2 classes. Like for example, you can think of the middle class being the apples and the outside class being the oranges, because also has the orange color, right? And you want to find out the region that separates the two, the apples from the oranges, right? So you try to learn that by adjusting the weights of these neurons, right? And you see you're trying to adjust the weights and so on and so forth. And you see eventually you discovered that, okay, this region of the space belongs to apples and this region of the space belongs to oranges. And, there are several examples. If you're interested, you can play it around for different cases. This is another example, right? In which the data was distributed, in this fashion for the 2 classes, and it, eventually classified it. And you can see, as you're going deeper, here you're learning simpler features, and here you're learning combination of features that is helping you classify one thing from the other. Okay, I mean, you can have a lot of fun playing with it. So I guess I'll stop for that for now. All right, so moving on. Let me quickly give you some of the examples of my work or things that I have been involved with in the recent past. So, yeah, just keep. Oh, what happened? Okay, wait. Let me reshare the screen. All these technical glitches, All right, where's, yeah, this one. Okay, all right. So some of the examples that I have been involved in the recent past, we were involved in this 3D eye segmentation challenge, in which we had the team named NanaNet, composed of myself, my collaborator, Dr. Abhinav Dal, and student intern, Jyot. And we were 3rd place winners of eye tracking 3D eye segmentation challenge in 2021 that was sponsored by Facebook. And the results were officially announced in October last year in the International Conference on Computer Vision. Now, the task was, given, for example, the point clouds, that means, given the locations in space of the eye region, you want to identify which is what. For example, if this is, where is cornea, where is iris, and so on and so forth. Now, since we had some computational problems, so we trained our algorithm with a much lesser number of points. So these were essentially the data given by the organizers, but this is what we trained the algorithm with. So this is one example output. So this is the input to the algorithm, and at the output, we were able to find out, okay, this region corresponds to one part of the face, this region corresponds to another part of the face, and so on and so forth. Okay, and we were third place winners in this challenge, right? Now, also, we, me and my another collaborator, Ms. Washio, we participated in this palm trees detection project. There was a palm tree detection challenge, Vista challenge, that was held in collaboration with Mohammed bin Rashid Space Center and Amazon Web Services and the Dubai Air Show. And the task was to detect from the satellite images where are the palm trees located, right? We managed to get into the top 6 teams, and we were the only team that was not belonging to, that was not a company entry, right? We were just individuals, right? But the other 5 teams were actual companies that were working on this project. So just getting to the top 6 was indeed an achievement by itself. So, for example, these were the palm trees and satellite images. These are the actual, location of the center of these palm trees, right? This is center of the palm trees, center of this. This is the center of this palm trees, and so forth. And our algorithm was able to identify, okay, the locations in the scene for the palm tree. For example, it figured out this one is a location, this one is a location, this, see a light dot over here, this is another location of palm tree, and so on and so forth. And then, there's some other examples, like, this is another example, this is yet another example. And this is an interesting one, because when we were labeling the palm trees, so this is during the testing time, we actually missed, there is a small palm tree over here, right? We actually missed it, but the algorithm was able to identify that there's a palm tree over there. Then also, this is another work that I was involved in recently. We named the work the Completing the Incomplete with the Art Da Vinci. That means completing the incomplete with the artificial Da Vinci. And what it does is, like, it completes the missing information in images. Like, for example, let's suppose you went to this beautiful lake, right? There was a signboard over here. You want to get rid of the signboard. Who likes signboards in pictures? So you can, let's say, draw a box on the signboard, and then the algorithm filled in the missing information. And you can see, it looks very realistic. Here, this is the picture of Venice. And let's suppose, there are some writings on the wall that you want to get rid of, right? Or, some regions that you want to get rid of. Just mark the mask, and, it just reconstructed the missing parts. Here, you reconstructed parts of the face, right? Here, it reconstructed again parts of the face, right? And so on and so forth. And yeah, and this was published in 2021 in the proceedings of Winter Conference on Applications of Computer Vision. Okay, I can quickly show you a demo, and then I guess I will stop. So this is the demo that I coded based upon the work that my student intern Gaurav did in collaboration with my other collaborators, Dr. Abhinav Dal, Dr. Subramaniam Morala, and myself. So let me quickly show the demo, and then we will conclude. And let me do a new share, and I guess this is, no, not this. Let's say I do a shared screen, and there's a demo. Yeah, this is a demo. Okay, right. So you see, you see this. You have this demo in which you have several images which you can scroll through, and you can let's suppose on this girl, like I paint or I generate a random mask and I will try to then finish the missing information, right? So let's see, it's processing. So, and the interesting thing is, like, it's doing on a laptop, and my laptop is not that strong, right? On a server, it's going to be much faster. Yeah, it's working. Just bear with me, like it takes like 10 seconds. Okay, now you can see, it just reconstructed the missing portions of the lady, right? Let's say let's say another example, right? So it's working. Just a few more seconds. Yeah, see, so it just reconstructed the missing regions of the girl, and there are some blemishes, right? But then this was the missing data, and the computer was like the model was imagining what that missing data would look like, right? And it saw, for example, the parts of the hair, and it figured out, okay, it needs to complete here in this direction, and so on and so forth. All right. So let me presentation in one more go. Okay. All right. Okay. So some other works that I have been involved in the past, and for example, applications of machine learning, the deep learning to face verification. I've done some work in that direction. To EEG signals that are small signals on the brain, for facial expression recognition, human activity understanding, earthquake engineering, power systems, power generation, automated inspection of insulators, and so on. Okay. All right. So I will conclude, and yeah, that's the end of my talk. And I guess I just finished on the dot. So if you're interested in collaborations, this is my email address. You can reach me out on this email address. And if you have any questions, please ask me now. Thank you.